Now we finished the three speakers' presentations. So well organized and very useful and excellent presentations. Thank you for all speakers. Now the time for question and discussions. So we will first discuss about the topic. First speaker, Mr. Alfonso. Okay, so are there any questions or comments for the first presentations? Okay, actually I have one question. So it is a very interesting presentation because you showed the actual behavior of structures, and I don't know. My question is that when you design the temple, so it is in between the cross point, at cross point. So how did you consider the effect of gravity load when you design the grid, the temple?
Sorry, you said the type of.
How do you account for the effect of gravity load? Gravity load, not earthquake load, for the temple.
I'm sorry, I don't understand. You mean vertical?
Okay.
Let me explain a little bit. You know, in the configuration that you used for the dampers, you had a type of chevron and inverted chevron type, and the dampers were placed between at the joint location. So if there is a gravity load in the diagonal member, the damper, deformed plates would take some compression if there is an axial force. The question is related to if you experienced or if you found any component of vertical force in those dampers.
Okay, yeah. The device, it is designed for lateral displacement. However, due to the natural shortening of the structure due to a strong earthquake, these devices would receive some vertical forces as well. But since the distance of the height of the U-shaped flexural plate, it's about like 8 or 10 centimeters, they allowed a vertical deformation enough for not surpassing the elastic, the breaking point of the elasticity. So none of the pieces were affected by vertical deformation. I think it's probably marginal. It's probably so little, the vertical deformation, that it will not bend the U-shaped flexural plate.
Okay, thank you. I have also one question. For the type of dampers that you utilized, in your test, I saw one of the tests that was showing a failure element. I was wondering how many cycles of hysteresis loops that specimen experienced before the failure. Do you remember any information regarding the number of hysteresis loops?
No, I'm sorry, I don't have that information. It was taken to the breaking point totally beyond a normal earthquake, beyond any normal period or strength, but I don't know what was that point, what was the equivalent to an earthquake,
Okay,
but probably something non-existent.
Thank you very much.
Okay. So.
Yeah, hello. This is engineer from the Chang Minwoo consultant. I'd like to ask a question to Mr. Barroilhet. I hope you pronounce right. Well, I'd like to know what is the maximum displacement and the lateral maximum displacement of the damper.
Of the damper itself or the whole building?
Both. both please.
For the whole building, it's between 40 and 45 centimeters on the top of the building, and this is a about roughly 200 meters high building. Now, for the displacement of the fixture itself, it's between 5 to 6 centimeters of lateral displacement before going into beyond the elastic point.
Thank you very much.
Other question or comment? So I have one more question. I hope you understand my question. Okay. The aspect ratio. So your building is very slender in short side, and in the long side, the aspect ratio is okay. But in short side, it's very, very slender. I look like so. How much is the aspect ratio in this shorter directions in your building? What is the ratio of the height to the short dimension?
The deformation between the height of the short
you have
side?
a height, building height, and also you
The
have
ratio.
building dimension. Okay, short dimension.
It's, as I mentioned, it's 45 centimeters out of 200 meters.
20.
45 centimeters out of 200 meters. So
What is
ratio,
number?
it's,
About 20 or?
As I gathered, the question is the aspect ratio of the tower that utilize your dampers. You know, the height to the width, footprint dimension of the building. How much is that ratio for the building that you design? Is that correct?
Exactly. Yeah. In short direction.
okay, you mean the width
Yeah,
versus
width.
the length of it,
Yeah.
right?
Yeah.
It's probably the double. It's about the double the length compared with the width of the building. But it's facing.
Height divided by the width, by the smaller dimension of the building. Height of the building divided by the smaller dimension of the footprint.
I don't know. I'm sorry. I'm not sure.
Okay.
Like, I need to do the numbers about that. I don't
Okay.
have that ratio.
Yes. Okay. Are there any more questions for first topic? Okay. Thank you for your answer. Okay. Now I would like to move to the second topic. Dr. Ryu's presentations. So, are there any question or comment?
Actually, I have one question.
Okay, you have question.
Yes. I was wondering regarding the dampers that you were planning to utilize for some projects in Korea. Did we really get to the level of demand that requires utilization of dampers, and if that demand level can create severe cracking or damage in the conventional link beam element?
Okay, Dr. Yu.
Sorry, pardon?
Okay, my understanding is that you did not clearly present the demand. So you showed the capacity of the steel. So what is the demand in your applications? So you
Maybe I explain a little more. You know, when you analyze your building, if you, instead of the link beam, if you use a conventional link beam, not a damper, there is a rotational demand at the end of the link beams. And in a high seismic zone, this demand can exceed the capacity and also create a lot of cracking or damage in the conventional element. However, it depends on the amount of the deformation that is required, and it depends on the seismicity of the area that the building is located at. So I was wondering if in Korea such a high demand exists for utilizing dampers in the link beams. That is the question.
Sorry, I understand. I don't understand. Our developed damper is efficient to a seismic load, and the damper is fractured, and we can reuse the damper, and we can reuse the building.
이제 저런 얘기죠. 그러니까 이제 우리나라 지진 상황하에서 그 정도의 많은 디포메이션이 필요하냐, 또 필요하면 어느 위치에서 필요하냐 하는 것을 좀 얘기해 줄 수 있냐, 이런 얘기입니다.
Actually, in Korea, the earthquake is becoming in the magnitude 6. Our developed damper is, if our developed damper is used in building, we guarantee the safer and stable housing for you.
Okay, I gather that that has to be done later, or you will utilize the damper for high seismic zone. Anyway, I think that is a quantity that needs to be taken into account. Anyway, thank you for your work and presentation. Okay, now.
So, any other questions? Okay, so next move to third and last presentation. Are there any questions or comments? Okay, so okay.
Yeah. I have a question for Professor Kim. You utilized the diagrid structural system, and my understanding is that, correct me if I'm wrong, that in the course of nonlinear analysis or linear analysis, the model anyway passed the linear limit, and there should be a mechanism for yielding of the diagrid elements. Since in a diagrid system, there is no column at the perimeter to carry the gravity load, I was wondering how the system to carry the gravity load was provided, or if your model indicated failure after reaching the buckling load of the diagrid elements.
It's nearly good and tough questions. Actually, I talked about this issue with Dr. Poyer in CSI Berkeley. We developed the Perform 3D. Actually, because diagram member, actually the Dr. Moon is expert on diagram member system, it takes a gravity load, basically, because there's no column. And also, it takes a wind or a seismic load. For wind load, we designed the system in elastic, so it'll be okay. But for the seismic, actually we use the R factor for the design. That means R means we allow the yielding, right? But in case of yielding, actually, if the actual member going through yielding, because it takes a gravity load, and it's easily to buckle. And because the brace system, the gravity load takes, column takes gravity load, and the brace member itself only takes lateral load, as mentioned in the previous presentation. But the member actually takes two actions in just one member. So at the beginning, I think we should not allow any inelastic behavior in the member. But in this case, the seismic design may be uneconomical, because when I show the force distribution, and we use aspect of 4, so that means we have to design for 4 times more increased design forces. Then it will be very uneconomical member size. So actually, this is not the final solid analysis research result. We are just in the middle of research, and we are first think about the yield mechanism using the member. And then I probably move on to the next stage. So I think then for the diode system, we may need some another way of energy dissipation, not allow in the inelastic behavior in the diode members. Yeah, it's a very tough question, so I'm still working on it. Thank you.
Okay, any other questions or comments? Okay, if there are no other questions, then we are going to conclude these sessions. So I appreciate for the kind attending from floor, and also good presentation by the speakers. Thank you very much.